Hi, my name is Américo Cunha. I'm from Rio de Janeiro State University, and I will present this work entitled Parametric Probabilistic Model for Predicting Creep Remaining Useful Life. And this was done in collaboration with my student Victor Maldonê and Dr. Carlos Frederico Trotomati from Electrical Energy Research Center, CPL. Up to today, humanity is so dependent on high temperatures to generate energy, as you can see here in this graph. Most of the energy generation processes depend on high temperatures. And this will not disappear in the nearby future because the demand for electricity in Brazil is increasing a lot. So the demand for high temperature processes will increase in the same rate. And what's the problem and the challenges associated with the use of high temperatures process for energy generation? In order to increase the efficiency of the process, you need to increase the temperature difference, okay, between the lower the lower temperature and the high temperature. And this causes the material sometimes to operate close to the limit, and creep may become a problem in this scenario. So what are our objectives here in this work? We intended to propose an uncertainty quantification framework for parametric creep life prediction models. We intended to quantify the uncertainties associated with the input parameters of these models and identify which of the parameters of a family of creep models are most significant for the prediction, okay? So just a few comments about creep. It's a standard, it's a common phenomenon and considering creep in engineering analysis is a standard procedure, but I think it's worth of comment some of the characteristics of creep in here. It's characterized by slow and progressive plastic deformation. It's a time-dependent problem, which also depends on temperature. And it's very common in several industrial processes which deal with high temperatures. Here in this slide, you can see a family of parametric models used for creep modeling, okay? These models relate temperature, mechanical stress, and rupture time into a single equation. And you can see the left side is a parameter-dependent model, which is a function of the mechanical stress, okay? We are going to model this parameter by polynomials, okay? By polynomial functions, okay? And the constants of the model will be determined by experimental data obtained from a data set which relates the rupture time with the mechanical stress and the temperature. The framework we are proposing here is complex and summarized in this picture, okay? We are going to construct first a statistical model to describe the left side of those equations, okay? The dependence of the parameter with the mechanical stress. Then we're going to conduct sensitivity analysis to identify the most sensitive parameters. And these parameters will be modeled, okay? The uncertainties in these parameters will be modeled by a using a probabilistic approach. Then we are going to propagate uncertainties to the model and compute some statistics. And finally, we are going to use a model selection criterion to identify the best model, which represents the data we have here, okay? So first, we need to treat the data. You can see here the data for a chromium molybdenum vanadium steel material, okay? This is the Larson-Miller parameters function of the mechanical stress. And we first inserize the data to eliminate some outliers. After that, we use this treated data to determine a polynomial expression to represent the left side of those equations for parametric prediction, okay? We use as target model polynomial degrees up to 80th degree, okay? And we apply a cross-validation procedure to identify a parsimonious model with some robust characteristic. Okay, we combine cross-validation with sparse regression. Okay, using the sequential threshold least square method, and after that we are able to construct hundreds of polynomial functions. Okay, and select among these plethora of polynomial candidate functions those which are best represent the data following a certain model structure. Okay, you can see here the polynomial for Larson-Miller, for Orcher-by-Dorn model, and for Manson-Sukov. Okay, Larson-Miller, you have a 1-degree polynomial. This is the sparsest representation following this model structure. And when we follow the other two more complex model structures, we obtain quadratic polynomials as the sparsest polynomial functions compatible with the data. Okay, then we proceed with a global sensitivity analysis using Sobel indices. Okay, and we compute Sobel indices here using both Monte Carlo simulation and polynomial case expansion. We use Monte Carlo as a reference for the first order indices, and we use the polynomial chaos surrogate to compute the high order indices because it's more stable against the cancellation errors. Okay, you can see here the first order indices for Larson-Miller model, for Orcher-by-Dorn, and for Manson-Sukov. But you see a relatively small contribution of the parameters, especially the parameters of the regression, for the response of this model, which is the rupture time. But when we consider the high order effects, which are encapsulated here in the total Sobel indices, you can see that the joint effects between the parameters here are very pronounced. Okay, these models, the individual effect of the parameters is not important, but the joint effect is very significant. Okay, except in Larson-Miller, the A1 coefficient, okay, the high order coefficient of the first order degree polynomial. Okay, in the Orcher-by-Dorn, the quadratic coefficient is not so important, as well as in Manson-Sukov, but the other parameters, their joint effects are very expressive. Okay, so we are going to pick the polynomial coefficients which affect a lot in a joint way the model response, and we're going to model them as Gaussian correlated parameters. Okay, and then we're going to propagate this uncertainty to the rupture time using Monte Carlo simulation with 10,000 samples. And after that, you can see here the response, the rupture time. Okay, you can see the histograms and some statistics and experimental data reference. Okay, and you see that in this case, in all the operating conditions of temperature and pressure that we observed, you can see a exponential type of distribution for the rupture time, and this perceives for the other two models. Okay, the three parametric models, in the three cases, you can see a exponential type of distribution for the rupture time. We could also use this framework to estimate probability of a rupture. The probability of the rupture time be smaller than the reference, the experimental reference. Okay, and you can see that depending on the operating condition, this probability could be as high as 91%. Okay, for Larson-Miller, 85% for Orcher-by-Dorn, and for Manson-Sukov. Okay, you see that this may vary a lot and be very high depending on the operating condition. Okay. Finally, we have a family of models. Okay, all of them were calibrated with the data and enhanced with probabilistic components to be able to capture the uncertainty effects. But which model should we use? What's the best model? Well, we use two different model selection criteria here to determine the best model among those three I presented here. And according to archaic information criteria and BIC criterion, Larson-Miller was the best choice, okay, according to both criteria and using the data set I showed you before, okay. To conclude, we observed that the isolated effect of the input parameters in that family of predictive models for creep, the isolated effect is relevant, okay. The joint effect of the parameters is important. For Larson-Miller, the coefficient of the angular coefficient of the polynomial is not important. For the other two models, the quadratic coefficient is not important. We observed that these models present a tremendous sensibility to the statistical dependence of the input parameters. Okay, if you change the input distribution, the output varies a lot. And in all the numerical experiments we conducted, in the rupture time presented the exponential distribution. Okay. So I wish to acknowledge the financial support of CEPEL and the Brazilian funding agency, CNPq, CAPES, and FAPERJ. I acknowledge your attention, and if you have any questions, I will be happy to answer. Thank you.